Presented by Science at NASA. Experts say solar max is due in the year 2013. When it arrives, the peak of the 11-year sunspot cycle will bring more solar flares, more coronal mass ejections, more geomagnetic storms, and more auroras than we have experienced in quite some time. On the weekend of July 14, 2012, skywatchers around the world got a taste of things to come. It was mid-Saturday in North America when a coronal mass ejection, or CME, crashed into Earth's magnetic field and triggered the most sustained display of auroras in years. For more than 36 hours, magnetic storms circled Earth's poles. Northern lights spilled across the Canadian border into the United States, as far south as California, Colorado, Kansas, and Arkansas. In the southern hemisphere, skies turned red over Tasmania and New Zealand, while the Aurora Australis pirouetted around the South Pole. The source of the CME was giant sunspot AR 1520, a seething nest of tangled magnetism more than 15 times wider than Earth itself. On July 12th, the sunspot's magnetic field erupted, producing an X-class solar flare and hurling 1 billion tons of electrified plasma toward our planet. NASA's twin stereo probes and the European Space Agency's Solar and Heliospheric Observatory monitored the CME as it billowed away from the Sun. Using those data, analysts at NOAA and NASA successfully predicted the cloud's arrival time. It would take almost 2 full days for the CME to cross the 93 million-mile void between Earth and Sun. The CME's impact sharply compressed Earth's magnetosphere, briefly exposing geosynchronous satellites to solar wind plasma. The shaking of Earth's magnetic field caused compass needles to swing, just a little bit, and prompted electrical currents to flow through the soil at high latitudes. Fortunately, the strike did no harm. Satellites survived and power grids stayed online. Next came the light show. As the CME's wake washed across Earth, the polar regions of our planet lit up like a Christmas tree. Red, green, blue, and purple auroras capped both ends of the planet, glowing, dancing, and ultimately spreading to places where auroras are seldom seen. In Arkansas, for instance, there was a faint glow off and on for most of the night, reports Brad Emfinger from a little town called Ozark. Around 3 a.m., there was an outburst of red and purple plainly visible to the naked eye. In Pawnee Grasslands, Colorado, photographer Robert Arnn saw the northern lights for the first time ever. As soon as I stepped out of the car, the sky looked like it was on fire. Then the moon, Venus, and Jupiter rose together in the east. To see the conjunction and the auroras side by side was incredible. Meanwhile, at the other end of the planet, auroras were going crazy over the South Pole, reports Robert Schwartz at the Amundsen Scott South Pole Research Station. We enjoyed the show under crystal clear skies with an air temperature of -105 degrees Fahrenheit. In Ashland, Wisconsin, on the other hand, John Welling watched the show in his shirt sleeves. Tonight, it was absolutely the best, with a comfortable temperature of 78 degrees Fahrenheit, and northern lights dancing overhead. The X-flare definitely lived up to the hype. From one end of the planet to the other, spanning more than 90 degrees of combined north-south latitude, 183 degrees of temperature, and 360 degrees of longitude, this was truly a global space weather event. And it was just a taste of things to come. The Sun-Earth connection is heating up.
What is the Aurora Borealis and the Northern Lights? The Aurora Borealis, the Northern Lights, is much more than pretty lights. It's a perfect blend of solar wind and magnetic fields. Let's check out the science behind the Aurora Borealis. Magnetic field and rubber bands. The Earth has a magnetic field surrounding it because of the iron-nickel core at the center of our planet. Understanding this magnet field is essential to understanding the science behind the Aurora Borealis. The magnetic field exiting from the core is responsible for the magnetic north and south poles we use when we navigate with a compass. It also creates a magnetic force field around the Earth, which extends into space. As charged particles, electrons are negative, protons are positive. In the solar wind encounter the Earth's magnetic field, they travel along the field lines. On the sunward side, the field is compressed by the solar wind to be closer to the Earth. However, on the night side of the planet, the field stretches away from the planet like a tail. Eventually, the magnetic loops stretch so much that they break like an overstretched rubber band. A piece heads off into space away from Earth, while the other part snaps back toward Earth. The piece snapping back toward Earth accelerates the particles it captured into Earth's upper atmosphere. When these particles hit molecules in Earth's atmosphere, they trigger light displays depending on the altitude and energy of the collision. Most of the molecules in Earth's atmosphere are either nitrogen or oxygen, so they are hit most frequently. Colors produced may be pink, red, yellow, green, blue, or violet. Occasionally, orange or white are produced. Typically, nitrogen will produce red, violet, or blue. Oxygen usually produces green or yellow. Reds generally are emitted above 240 kilometers, greens at 100 to 240 kilometers, purple and violet above 100 kilometers, and blues at 80 to 100 kilometers.